Welcome to the session on operators and simulation of real coded genetic algorithm. In this session, we will discuss various operators that will be required for RGA. So here RGA stands for real coded genetic algorithm. We will first discuss about the selection operators, thereafter the crossover and mutation operators. The simulations of RGA will be shown using four functions that are Rosenbrock function, Hamel-Blau functions, Rastrigen function and Eckley function. And thereafter we will conclude this session. So before we start our different kinds of operators that are available for RGA, let us have a recap of the previous session. In the previous session, we found that when we are using binary coded GA for continuous search space, there are certain limitations. Those limitations are corresponding to the precision or sometimes the Hamming-Cliff problem. So, and moreover, the binary coded GA makes the continuous search space into discrete. Looking at those limitations, we targeted EC techniques that can be used for real parameter optimization. So in that category, we have gone through RGA, evolutionary strategies, particle swarm optimization, differential evolution, and etc. So all these EC techniques are used for solving real parameter optimization problems. We understood RGA using the generalized framework in which various operators and the processing of RGA we understand through this generalized framework. To understand the working principle of RGA, we have taken an example of a Rosenbrock function. We want to minimize the function, and for this particular Rosenbrock function we know where is the optima. So we started with the initial population. So here the important part was that we have to code the variable as a real number. Thereafter we use the selection operator, which is the binary tournament selection operator. After going through that, we found that we don't have to change or we don't need any new selection operator for RGA because these selection operator work on the fitness. So therefore the functioning is not changing since we have already calculated the fitness of each solution. Thereafter we discussed about the crossover operator. So till binary coded genetic algorithm, we have to deal with the binary strings. As soon as we work with the real numbers, so we need to change the crossover so that we can use it. In this particular section, we have gone through the various properties of single point crossover operator, such as the averaging property, and there was a spread factor beta. So those two properties were taken into the consideration, and the authors came up with the operators called SBX crossover operator. Thereafter, there is a polynomial mutation we talked about. In this polynomial operator, we found that the probability distribution function was nonlinear. Similarly, in SBX as well, the probability distribution function was nonlinear. That nonlinear distribution allows to create solutions closer to the parent solutions. And finally, we use mu plus lambda strategy as a survival stage as an example there. All these processes, as you can see, all these operators and evaluations, we have shown with the help of hand calculation. So we show every calculation for a one generation, and the same calculation we also showed with the help of graphical illustration. So this graphical illustration helps us to know or understand how these solutions will be moving towards the optimum solution. With this recap, let us move to the operators now. We start with the selection operator. As we know, selection operator need the fitness value of each solution to select good or above average solutions. we have various methods available with us. For example, we can use fitness proportionate selection, tournament selection, or the ranking method. And for combining the parent population and offspring population, we use mu plus lambda strategies. So all these operators which we use either before variation operator or after variation operator, everyone needs the fitness value. And this fitness, since this fitness value is calculated earlier, so we found that there is no change in those selection operators. So the selection operators which we have understood while learning binary coded GA or all of those operators are valid here. Now let us come to the selection to the crossover operators. Now crossover operators, here these crossover operator for real parameters, sometimes also referred as a blending operators. So let us start with the first crossover operator, that is the linear crossover operator. As you can see here, this is one of the earliest implementation shown by Wright in 1991. So for our simplicity, we are considering P1 as our parent 1, P2 as a parent 2. Now in this case, P1 will be equals to the ith decision variable for the solution selected in the tth iteration. Similarly, this is the ith variable for solution 2 and tth iteration. So before we move, we know that to perform crossover operator, we have to select 2 or more solutions randomly from the population. So in this case, we selected 2 solutions as it is given here as 1 and a 2 randomly, and we are representing these 2 solutions as P1 and P2. Now here in the figure, you can see that when you have P1 and a P2, this crossover operator generates 3 offspring solution. So the offspring solution 1 is actually at the middle of P1 and a P2. So we can say it is P1 plus P2 divided by 2. Now if we measure this particular distance and say this is delta, with the similar distance we created another solution. So you can see on the left hand side of a P1, offspring 2 is created. On the right hand side of P2, another offspring is created. Looking at the formula here, so offspring 1 which is at the middle of P1 and a P2, offspring 2 is on the left hand side of P1, and offspring 3 is on the right hand side of the P2. So as the representation I explained you earlier, this is for the ith decision variable and the tth iteration. Now in this case, as you have realized that 2 parent solutions are used to create 3 offspring solutions, as I am writing as 1, 2 and 3. Now what we do here is from these 3 solutions we choose 2 best solutions among the 3 solutions. So this is the way linear crossover operator works. It is one of the simplest implementation here. The another crossover operator which we have is called blend crossover operator. So this blend crossover operator is also known as BLX alpha. Now in this crossover operator, we assume that P1 is smaller than P2. So the same representation we are using for parent 1 and a parent 2, but with the condition that P1 is smaller than P2. Now in this crossover operator, we can see in this figure we have P1, P2, and then we have a delta. Similarly, we have the same quantity of a delta on the right hand side of P2. So in this case, the delta is decided as alpha times of P2 minus P1. And as you know, P2 and a P1 we are writing in terms of xi 2t minus xi 1t. Now looking at this particular figure, we can see that the solution can be generated from xi 1t minus delta to xi 2t plus delta. So basically, if we look at this region in the figure, in this particular region the solution is created, and that is created randomly in this region. So the offspring is created with the help of another factor called gamma, and this gamma is calculated with the help of alpha value and a random number ui. So using these two values we can found the value of a gamma. Now we know that ui is a random number, so this random number will be generated by the computer. Now in this case this alpha value, this is a user defined value, and we have to set this value here. Now looking at the equation of the offspring, you can make it out that the two solutions, we are using a scaling function such as 1 minus gamma times of parent 1 plus gamma times of parent 2. So this scaling we use it to create an offspring. So from this particular crossover operator we found that two parent solutions are creating one offspring here. Now since we have included this gamma into the creation of the offspring solution, so if we fix this value of alpha throughout the iterations, we can find that the gamma I is uniformly distributed for a fixed value of alpha. So this distribution, as I showed you earlier, so this is the distribution where a random a solution will be generated using BLX alpha. Now the question is, what could be the value of alpha? Because I can use 1, 0.5, 3 or 7, anything value I can use it. So in this particular study, the author found that if we use alpha is equals to 0.5, this particular value is working good for many test problems. So that's why a guideline or a thumb rule is developed that we can take alpha value. However, we can change this value as per our problem and simulation. Now let us see what is the characteristic of this operator. So the equation, the original equation in the previous slide is written here. So let us move some quantity on the right hand side, keep some quantity on the left hand side. So this particular equation is modified as what you can see here. Now the important point in this particular equation which we have rewritten, so in the rectangular box you can realize it is similar to the difference between P2 minus P1, meaning that the difference between these two parent actually decide what could be the new solutions. So therefore it says that if we are going to use BLX alpha, the search is adaptive in nature. How? If suppose we are starting, so at the beginning when the solutions are randomly generated in the plane of variable, in that case we pick two solutions randomly. So generally these solutions are little far from each other. So when they are far, this particular difference will be large. Since this will be large, so the offspring solution that will be created will be little far from their parents. So this property will help us to explore the search space initially, and that is what we desire from EC techniques. But in the later generations, what you will see that the solutions will be close to each other. When they are close to each other, then the same difference will become small, and therefore the offspring will also be created close to the parent. So in this case, since the difference is small, we can say the search is focused. So this adaptive property is useful in all EC techniques if we can implement it. Simulated binary crossover is the third crossover operator. This crossover operator we discussed in detail. This operator uses the nonlinear distribution, probability distribution. You can see with respect to the value of beta I, there are two functions which are used. So if you look at this particular figure, so this is the value 1 So on the left hand side there is another function, another side there is another probability distribution function, and these two probability distribution functions are nonlinear in nature. The objective is the offspring should be created close to the parent solution. And how we can calculate the value of a beta I, as we have discussed earlier, that we will be integrating this probability, and this integration will give me the value of beta I. So integrating this means the area under the curve, as you can see here. So this area under the curve we can correlate with the random number given here as a ui. So after simplification we can get a value of a beta I based on random number. So if random number is smaller than or equal to 0.5, we will be using the first equation, otherwise we will be using the second equation. Using this beta I value, we used this beta I value to create offspring. So this equation is familiar to us. As we can see, these two quantities tells us about the average property, and then we have a beta which we calculated using the probability distribution function, and the difference between the two solution or two parent solutions. Here it is important to note that all this analysis we are doing by assuming that P1 is smaller than P2. Now let us see how this SBX operator behaves. So in this case, let me draw the curve for two eta c value. So this particular different eta c value we have gone through in the previous session. Now here we have two solutions. So using these two solutions, if we take different eta c value, so what will be the curve? So let me take eta c is equals to 2. In this particular case, this eta c for 2 value, it will be similar to this curve, and then it will move here and then come back here. So this is for eta c equals to 2. Now suppose we will take a larger value, say eta c is equals to 5. So what will happen, that as and when this eta c value is large, so you can see it is approaching the y axis in this way, then the mean, then again for the another solution it is approaching like this, and then finally coming here. So what we can see here is, for the two different values of eta c and eta c equals to 2 and a 5, we get two different curves. It is only because when we are integrating the probability, the area under the curve maximum could be 1. Now as you can see that if we are using the eta c, large eta c value, that indicates that there is a higher probability of creating new near parent solution. It is because of the nature of the curve. So when eta c is equals to 5, as you can see that the width of the curve is reduced, however its peak is increased with respect to eta c equals to 2. So in this case, when an offspring will be generated, so the solution will be close to the parent solution. In another case, when eta c is small, then we have a curve which is little wider than the eta c equals to 5. So for a smaller value of eta c, the offspring solutions can be created little far from the parent solution. Now let us come to the property, another property of SBX operator here. Now what we have done here is we have taken the difference between the two offspring solutions, that comes out to be the difference between the parent solution, and this is multiplied by beta. So in this case, what we can see that the difference between the offspring is proportional to the difference between the parent solutions. So, this is similar to the property as we have learned with the BLX alpha. So, in this case SBX operator also supports adaptive search. In that case, in the initial generation when solutions are little far, so the offspring solutions will be generated little far. Similarly, when after few generations, when solutions are moving towards the optimum solution, so they are close enough, and this difference suggests that the offspring solution will be generated close to their parent solutions. Now, let us take two cases here. In one case, as you can see in this plot, y axis the probability density and the x axis has parent 1, parent 2, similarly offspring 1 and offspring 2. So, since in this particular figure you can see that P1 and P2 they are little far, so what could be the distribution? So, if I redraw this, so this is coming out to be this. So, in this particular figure plot you can see that when the solutions are far, so these two probability distribution for P1 and a P2, since they are far, so the offspring solutions will be created far because the difference between P2 and a P1 is large. Similarly, if we take the another case in the right hand side figure, so P1 and a P2 are quite close to each other. Let us take the another case where P1 and a P2 are close to each other, which you can see on the right hand side. So, here, so the distribution will be similar to like this, as you can see here. So, you can see there are peaks and then the curve is like this. So, in this case what we will see that when P1 and a P2 are close to each other, the peak of the curve has been raised. However, the width of the curve is reduced as compared to the figure on the left hand side. So, this will allow to create our offspring 1 and offspring 2 closer to the parent solution. Now, the crossover operator, that is SBX operator, which we have discussed, what we found that it can generate any solution between minus infinite to plus infinite. However, if we want, what we want is that since the variable bounds are given as between the lower and the upper bound, we want that this crossover operator should generate solution within the bound. So, in this case a small change has been made in this crossover operator, in which the cumulative probabilities are calculated with respect to beta u and beta l. What are those quantities? So, these quantities are corresponding to the upper and lower bound of the variable. So, you remember that we generally integrate from 0 to beta I, but in this case we are integrating from 0 to beta upper and beta lower, so that we can generate a solution within the range of xi. Now, this beta u, beta L and a beta u we can find using the formula given here, which is the summation of the two parents minus 2xi lower for beta lower, and when we talk about the upper, so we have 2xi uppers, that is the upper limit on this variable, and the difference between P1 minus and P1 minus P2. In this case the denominator remains the same, that is the difference between P2 minus P1. Now, using this modified probability, we are going to calculate two quantities, which are beta prime 1, beta prime 2. So, similar to area under the curve, and we are equating with the random number, the same approach is used, but with while respecting the lower and upper bound of the variable. So, our modified probability distribution, as you can see here, that will change. When we integrate it, we can get two values of beta 1 and beta 2. So, this two beta 1 and beta 2 values we are writing here. In this case, the same formula, as you can see, this is the summation of the two parents, and we have taken 0.5 outside. So, this is nothing but the average, and then beta 1 prime we have multiplied with the difference. Similarly, for the offspring number 2 we have average property, then plus. So, here you have to make sure that it is beta 2 prime. So, another beta for the upper limit, and this is the difference between the two parents. So, in this way we can generate two offspring solutions that will respect the bounds for the using the SBX crossover operator. So, let us take two things now. First, let me take the unbounded. So, unbounded means that the SBX crossover operator can generate a solution from the limit minus infinite to plus infinite. So, in this case you can see that this particular curve, which is coming from the infinite going here, and then this is coming here and then going here and then going towards the infinite. So, this is the probability distribution you can expect when the solution is generated from minus infinite to plus infinite. Now, let us take the bounded. So, bounded means that the SBX crossover operator will generate two solutions between the bound. Now, in this figure you can see the lower bound is given as well as the upper bound is given. So, how this particular solution will behave? So, here this will be, so let me start from the bottom, and then it will follow the similar trend here. It will come at the middle now, it will go little higher, and then it will finish here. So, this kind of a distribution for the bounded region, when SBX is creating a solution between lower and upper bound, you can see as soon as we are fixing the lower and the upper bound here, so the peak is actually, it has gone little up as compared to the bounded one. Why? Because the area under this particular curve should be 1. Now, we have restricted this probability distribution from lower to upper. So, the peak has been gone little high. So, as of now we have gone through this SBX crossover operator, where we can generate solution from minus infinite to plus infinite, as well as if we want to include the bounds. So, there are some changes needed to calculate beta 1 prime and beta 2 prime using the random number. Now, we are moving to the another crossover operator, which is known as fuzzy recombination operator. This operator, as you can see here, it is similar to the binary crossover operator, which is, we say it's called SBX operator. So, when we fix eta c value is equals to 1, then both the operators will behave similar. So, what is the difference here? So, in SBX crossover operator we use nonlinear probability distribution on the either side of the beta. So, for beta equals to 1 we had one function, and when beta is greater than 1 we had another function. So, instead of that, as you can see from this figure, in this FR operator, triangular shape probability distribution function is used, and this its working is very similar to the SBX crossover operator. Now, in the figure you can see there is a term called delta. This delta term has a significance because you can see that this delta depends on the difference between the two parent. So, it means that FR operator is also has this adaptive search capability, in which when the solutions are far in the early generation, then the offspring solutions will be created little far. When parent solutions are close to each other, when they are moving towards the optima, then offspring solution will also be generated close to the minima. Now, using this D, we have a delta which is also has, let me write here as D P2 minus P1. Now this is the D factor, which is a user defined factor. So this we have to decide before we execute our function or our algorithm. So in similar to SBX crossover operator, we have eta c, we have a BLX alpha where we have to set the value of alpha. This operator has a one user defined parameter called D. Now all the properties what we have discussed earlier with the SBX operator, all these properties are held by the FR operator. Now let us move to the new crossover operator, which is called unimodal normally distributed crossover, which we in short say UNDX operator. This particular operator was proposed by Ono and Kobayashi in 1997. Now as you can see, this particular crossover operator need 3 or more parent solutions that will create 2 or more offspring solutions. So we will see how. Now offspring solutions are created using the ellipsoidal probability distribution. So one thing you can see here, that the crossover operators are using some kind of probability distribution functions to generate offspring solutions. So this ellipsoidal probability distribution function is used with one axis formed along the line joining the 2 of the 3 solutions. So here we are assuming that we are working in a 2 variable problem. Now let us see how it works. So in this particular crossover operator, we take 2 solutions as P1 and a P2 and we picked it randomly. Now when we pick it, we find a component called D, which is nothing but P2 minus P1. So this particular component D, as you can see in the figure, this is referred as the parallel component. Now using P1 and a P2, we find the value of PC. Now this PC is referred as the center of the 2 parents, which is nothing but P1 plus P2 divided by 2. So as soon as we find this center here, we pick the third solution, which is P3, and that is again randomly. And this P3, as you can see, that P3 is lying in this particular figure here, and the capital D we find, and this will represent the orthogonal component. So using these parallel and orthogonal component, this crossover generates an offspring. So you can see that X0 represent its X0, O stands for the offspring population or offspring solution. We have PC, which is the centroid, then we have a zeta D. So as we know, D is our parallel component, and then we have summations with respect to zeta and component of PIs, and of D is our orthogonal component. So as you can see that zeta and eta are the random numbers, and Pi is the orthogonal basis that span the subspace perpendicular to the D. So we are talking about all the orthogonal bases corresponding to the D, which is the perpendicular or orthogonal component. So in this way, this crossover operator works and generates new solutions for EC techniques. Now as of now, we have gone through various crossover operators. In the literature, there may be few more crossover operators, but when we design a crossover operator, we look for certain properties. So one of the desired property is that the mean of the population should not change. What we mean by that? That we know that most crossover operators do not use any fitness value. Since they are not using any fitness value, meaning that the crossover operator will not be performing any search in a particular direction. So that is random in nature, and this is evident from the crossover operator, whether it is a crossover operator for binary string or for a real number. All of them are stochastic in nature, and we perform the crossover operator. Now at this particular stage, what we want is a crossover operator that can generate offspring population that such that the mean of the population should be the same as the parent solutions. However, the variance can change. So, let us take one example here. So, let me take this is the mean here and we have various solutions. So, for just clarity I am taking the solutions little far, but if you try to find out the mean of these, so that it will become red these the red point. Now, let me take another case here. Suppose we have this mean and the solutions are close to this particular solution. Now, in this case what you can realize that in both the cases mean will not change. So, I am assuming that both the population have the same mean. However, for this particular for the case 1, let me write here, for this case 1 we have a larger variance, but for case 2 we have small variance. So, the crossover operator should be generated or developed in such a way that the mean should not change. Second desired property is that the population diversity should increase. So, in every generation we perform crossover operator. Now, what we can realize here that since we are performing the selection operator, so we are actually reducing the variance of the population because we are selecting only good and above average solution. In this particular scenario, the crossover operator should not reduce the variance of the population. It is only because that will lead to the premature convergence. It is because sometimes if there is an individual which is closer to the local optima, then this particular individual will get multiple copies and then after few iterations all solution will become same. But since it is close to the local optima, then the whole population will converge to this optima which we consider as a premature convergence. So, in that case our crossover operator should not reduce the variance because that will help us to keep the diversity into our population. Therefore, as we suggested, the crossover operator that should increase the variance of the population. As of now, we have gone through various kinds of crossover operator for real parameters. So, in 2000, Bayer and they conducted a study where they were comparing different kind of a crossover operators and the performance of these crossover operator was tested on a flat landscape function, so that they can understand what is the growth of the population. So, they are measuring the variance of the population. In their analysis, what they found is, suppose because they have taken 3 crossover operator SBX, BLX and FR, and we know that these are the 3 user defined parameters we have to fix before we move during the simulation. Now, on this flat landscape, what they found is if they keep SBX eta c equals to 2, BLX 0.06 and D as 1.095, the performance of the operator was similar, all these operators. Similarly, when they kept eta c equals to 3, BLX is equals to 0.5 and D value 0.707, the performance of all these crossover was found to be similar. So, these values suggest that there is a one characteristic parameter value for which the different kind of a crossover can behave similarly. So, that is a good study that help us to understand that this different kind of a crossover operator in certain situation can behave similarly. After going through various types of crossover operator, now let us move to the mutation operator, which is also one of the kind of variation operator. So the first mutation operator is the random mutation operator. It was proposed by Michalowicz in 1992. As you can see, the new solutions created, so yi represents the new solution or the new value for the ith variable, that depends on ri, which is the random number, and the difference between the upper bound and the lower bound. The interesting part of this random mutation operator is that it is independent of the parent solution. So we can say that this mutation operator is a random mutation operator, and since it is independent of the parent solution, it can create solution anywhere in the search space. So to modify this particular mutation operator, a small factor of a delta I is included into the formula. So what this delta I says that, now let us look at the figure here. Now this delta I says that on the either side of xi, that is on the left side and the right hand side, we have a uniform distribution. So when we decide the delta I, so this will tell me about how much perturbation. So we call it as a maximum perturbation. So this maximum perturbation is decided by the delta I value. So let us look at the equation now. This says that the solution yi created by the mutation is equals to the solution that is the parent solutions, and it depends on the random number and the delta I. Now when random number is smaller than 0.5, you know that we are talking about the left hand side of xi. When random number is greater than 0.5, then the solution will be generated on the right hand side of the xi. Now in this particular crossover operator, as a remark, we have to take care of the upper and the lower bound. Why? Because if suppose this xi solution in the figure, if this solution is say somewhere here, as you can see, so let me write this as a p, solution p. Now if we take a delta value something like this, then it means that a solution can, or the mutation operator can generate a solution which is beyond the lower bound. So in this case, what we say that suppose I consider a solution created by the mutation operator is yi. So if yi is smaller than the lower bound of the variable, then we will say yi is actually on the bound. So we are keeping this solution on the bound. Similarly, if the solution yi is greater than the upper bound, in this case we will keep this solution on the upper bound. So such kind of simple implementation, we can use it so that our solution generated by mutation should be within the bound. Another mutation operator, here we have non-uniform mutation. It is only because looking at the figure, we have non-uniform or non-linear probability function. We can see from this figure that the non-linear probability distribution is used. In this case, because of this particular spread, this non-linearity will allow the new solution to be created close to the parent solution. So this particular operator was also proposed by Michalowicz in 1992, and it says that the probability of creating a solution closer to the parent is more than the probability of creating away from it. It's only because the non-linear probability distribution function is used here. Now along with this non-linear probability function, there are some other terms that are also used. So as you can see, the new solution yi is created with help of the parent solution, plus there is a delta I parameter which is included. From the formula given here, we can see that the delta I depends on the difference between the two parents, and the another factor which is the 1 minus random number. So, Ri represents the random number, and the power of the random number depends on the current iteration. So, T is the current iteration and the capital T is the maximum allowed generations. So, in this case you will realize that when T is 0 means at the beginning the power of Ri is 1, but when T reaches to capital T, then Ri to the power will become 0. So, in this case the random number has no contribution in generating the delta I value. So, this T max, as I have mentioned, it is the maximum allowed generation, and the power B is the non-negative user defined parameter. So, you can see this B which is a non-negative, just to increase the number or to give the higher power. So, that will be affecting the Ri because everything is on Ri, that is a random number here. Thereafter, the one of the simplest cross mutation operator which we can think is using normally distributed mutation operator. From the figure you can see this is the Gaussian distribution. In this Gaussian distribution we have taken like sigma equals to 1 and the mean is at the 0. So, this is small perturbation, we can use it with the solution. Now, looking at the formula here, so yi, the new solution, is equals to the parent solution, but plus the perturbation using the Gaussian probability distribution, as you can see here. Now, as we know that if we keep changing the value of this sigma I, then the spread of the curve will change. So, therefore, we have to find this sigma I value, or we have to define it very carefully. So, your sigma I is going to be the user defined parameter now. Again, for this mutation operator, we have to take care of the lower and the upper bound. As a recap, if the solution yi is smaller than the lower limit, then we will keep yi as is on the lower limit. Similarly, if a solution is created out of the upper bound, then we will keep this solution on the upper bound. So, these simple conditions we can use it for our implementation. So, every time when a solution is mutated, it will be generated within the range of lower and upper bound. Come to the polynomial mutation. Polynomial mutation is discussed in the previous session when we solved, or we have an example, we understood the working principle of RGA. So, as you can see in the polynomial mutation, it is also following the same, that the new solution is created with respect to the parent solution, and the difference between the two, the lower and the upper limit multiplied by the delta I value. Now, looking at the figure on the right hand side, you can see again the non-linear probability function is used, so that it will allow the new solution to be created closer to the parent solution. Now, in this case, the probability distribution, as you can see here, it is used, and when we equate the area under the curve, as you can see in the figure on the right hand side, we can calculate the delta I value. So, this delta I value, as you can see, if random number is smaller than 0.5, we have one formula. When random number is greater than 0.5, we have another formula. We have come to the simulation of RGA now. Let us see how this RGA works for different kind of problems. We will start with the Rosenbrock function, as you can see here. So, we want to minimize the function. So, this Rosenbrock function is written in terms of n variables, and the generic form of the Rosenbrock function is given here. The limits of the variables are taken as from -5 to plus 5. Now, two variable problem, as you can see in this figure on the left hand side, the y axis is taken as the logarithmic of the function, so that we can see the surface of this function, and in x and x2 plane we can see the contours. For this particular function, the optima is lying at 1, 1, and the function value is 0. So, in the first simulation, we kept the number of variable as 2, population size 40, number of iteration 200, probability of a crossover we keep it high because it has so many local optimas. We are keeping the probability mutation with the thumb rule 1 divided by n, n stands for number of variable, so it comes out to be 0.5. Then we use binary two-num and selection operator, and we also use SBX crossover operator to generate new solutions. So, here eta c value is 15 and the polynomial mutation is used, which has a eta m value 20. Finally, we used mu plus lambda strategy here. So, when we generate the initial population, you can see on the right hand side the blue dots are the initial random solutions which are generated in x1 and x2 plane. So, we call it is a random initial population. So, let us start with the simulation here. Now, as you can see, the solutions are distributed, and in 15-16 generations the solutions are already close to the optima, and close to 100 generation we got the solution. So, let us see one more time so that we can understand how quickly these solutions are converged to the optimum solutions. Since these variables are represented as a real number, so any precision is possible, and that is why RGA with the help of SBX crossover operator and polynomial mutation we got the solution early. Now, let us see the progress. So, the progress here is shown with respect to the best solution in the population. So, you can see in the y axis we have a best fitness in the population in every generation, and x axis is our generation. So, here initially we can see a drastic improvement, and thereafter since we have already close to the optima, so the performance is, or the improvement is less. So, as you can see, the performance is quite good at the in the initial generation, and even at before 10 generation we are very close to the optimum solution here. In the next simulation, we are solving the same Rosenbrock function. We have taken the number of variable as 4. So, in the last example we took 2 variables, now the number of variable is 4. Population size we kept it same as 40. Similarly, the number of generation is 200, probability of crossover is 1. Now, the probability of mutation is reduced. It is because we are using one thumb rule, that the probability of mutation is equals to 1 divided by the number of variable. So, now it is 0.25. The same set of operators such as binary, two-num and selection, SBX crossover operator, polynomial mutation and mu plus lambda strategy are used. Eta c and eta m values are 15 and 20 respectively. Since it is a 4 variable, so we cannot see the simulation with respect to the contours of the function. However, if you look into this figure, we can see that the best fitness initially was close to say 67, and it reduces drastically by say 23 generations, and then with a small improvement and close to 60 generation we got the optimum solution. So, let us see how it worked. So, we can see the improvement is drastic at the early iteration, early generations, and then slowly it is reaching to the minimum. Now, you can see the 0 is written here, and before 60 generations the RGA already found an optimum solution for 4 number of variables for Rosenbrock function. Now let us move to the another function, which is Himmelblau function. This function is a 2 variable function, as you can see on the top, and the bounds on both the variables is from -5 to +5. Looking at the surface on the left hand side, so this surface is based on the Himmelblau function, and if we look at the contours, you can locate 4 optimas. So basically it's a multimodal problem, as I have mentioned on the right hand side. So it's a multimodal function which has 4 minimum point. Now you can see that it has minimum point at 3, 2. Similarly, you have other 3 optimum solution where the function value is 0. In this case, we kept the population size 60, which is little larger than the Rosenbrock function, just to make sure that we are solving a multimodal problem here. Number of a generation is kept 200, probability of crossover is 1, probability of mutation is 1 by n, as this problem is 2 variable. So PM is equals to 0.5. We are using the same set of operators such as binary two-number selection, SBX crossover operator, polynomial mutation, and mu plus lambda strategy. Now since it is a 2 variable problem, we can show the simulation here. Now looking at the figure on the right hand side, this is the generation 1. This means we have this initial population which is generated randomly in the x1 and x2 plane. So let us see how these solutions will progress towards the optimum solution. Now as of now, the solutions are distributed along 4, but when we reaching to the 15th generation, the solution were at 2 peak, and after 50 generation we can see all the solutions are converged to the 1 peak. So here the advantage is that you can see the solutions are quickly converging to the optimum solution, but the disadvantage is that all the solutions have converged to the 1 peak, as we have discussed earlier with the multimodal function, that we should find out all the peak using EC techniques. Since we do not have any fitness sharing kind of criterion here that will help us to solve multimodal problem. So this is the best example we can see, that if we want to solve multimodal problem, then we have to include some features, for example fitness sharing, so that we can find the optimum solution at all 4 positions. Now let us move to the Rastrogen problem. As you know, this problem is difficult to solve because it has many local optimas and a 1 global optima. For an n variable function, we can have an objective function which is given on the top, and the bounds on each variable is from -5.12 to +5.12. Now looking at the 2 variable function here, the surface you can make it out, there are so many local minimas, and from the contour itself it is clear that this problem is a difficult problem. So the global optima for this problem is lying at the origin, and the function value is 0. So let us solve this Rastrogen function or a problem using RGA. Initially we have taken 2 variables, population size 60, number of generation 200, probability of a crossover 1, probability of mutation 0.5 because number of variable is 2, and the same set of binary two-number selection, SBX crossover operator, polynomial mutation, and mu plus lambda selection strategy. Now the figure on the right hand side, you can see the solutions are randomly generated, and let us see how this RGA will work for this kind of a difficult problem. Now from the simulation you can see the solutions are quickly moving, and in less than 30 generation we got the optimum solution using RGA. So that is the advantage when we deal with the real numbers and when we have efficient crossover and mutation operators. So again you can see how quickly the solutions are converged to the optimum solution. Now coming to the progress, let us see how the progress is visible or we can observe with RGA. Now initially it is started and within 10 or 15 generations the solutions are already on the optimum solution, and with the generation the rest of the solutions are converged to the optimum solution. So let us see one more time here how quickly the solutions are converged to the optimum solution. So within 15 generation the optimum solution was found by using RGA. So we can see that RGA is one of the efficient EC technique for solving real parameter optimization problem. In another simulation, we have taken the number of variable as 4, population size 60, number of a generation 200, probability of crossover 1, probability of mutation 0.5, and the same set of operators for selection and variation. Now since it is a 4 variable problem, we cannot see the simulation. However, we can see the progress as it can be seen in the figure. So it is started from say 25, close to the 25 value, and almost close to 50 generation there is a drastic improvement in the fitness, and thereafter since we have reached to the optimum solution, so the progress can be seen as a straight line. Now let us see the simulation, the progress simulation. So here you can see how quickly the solutions have converged, and almost after just 50 iterations we have reached to the optimum solution. So after close to the 90 generation we have a little improvement, that is just we are improving our optimum solution using RGA. So in this case we know that Rastrigine function itself is a difficult problem. Even we have increased the number of variable from 2 to 4, RGA is efficient to solve such kind of difficult problem where you have multiple local optimum solution and one global optimum solution. We also perform this RGA simulation for Rastrigine function having 10 number of variables. The population size is 60, number of generation is 200, probability of crossover is 1. Now probability of mutation is 1 by n, so 0.1. It is because the n is 10. Basically the number of variable is 10. We use the same set of selection operators for running the RGA. Now let us see the progress. As you can see, the best fitness started somewhere close to 130. It is keep on improving here, and just after 80 generation it is almost like a straight line, and there are further improvement close to 180 generation. So let us see what is the progress here. Now you can see the progress is steady and the solutions are improving. So best fitness is keep on improving with the number of generation, and now after 80 generation, as we have seen earlier, there was no improvement, and then there was a little improvement after 140 and 180. Important point here is that for 10 variable problem, we can see in this figure that still we are little far from the best fitness, which is 0, which is the optimum solution for the given problem. So in this case, if we want to improve RGA, we can work with the more number of population. So currently we have taken 60. So we can take it little larger. Why? Because the number of variable is 10, which is a large number. Similarly, number of a generation can be increased to see how this RGA will perform. Come to the Ackley's function. Now Ackley function is again a 2 variable function. Looking at the equation, you can see or observe that this function is going to have multiple local optimas along with the global optima. The variable bounds are given as between -5 to +5 for both the variables. Now look at the surface of Ackley function. Now small ups and downs in the surface suggest that there are many local optimum solution. looking at the contour of x1 and x2, that says that yes, there are many and we have a one global optimum solution. So, the optimum solution is at the origin, which is 0 0, and the function value is 0. For running the ACLE problem, we took the population size of 60, number of generation 200, probability of crossover is 1, probability of mutation is 0.5, and we have a SBX crossover operator with eta C15, polynomial mutation 20, and mu plus lambda strategy we have taken. Now, here since it is the repetition, we did not mention that we have also used the binary tournament selection. So, binary tournament selection operator is also used here. Now, in the generation 1, this is how the population members are distributed in x1 and x2 plane, which are randomly generated. So, let us see what is the simulation. Now, looking at this, how quickly the solutions have moved to the optimum solution in less than 30 or a 20 generation. So, once it is generated, now you can see within 5 or 10 generations, the solutions are actually converged near to the optimum solution. So, RGA we can say that RGA is able to solve the problems, such kind of a problems which has so many local optimas and one global optima. Let us come to the progress. Now, in this progress, we can see that how the fitness is improved quickly, and close to 15 number of generations, we have already reached to the optima, and therefore, afterwards there is a straight line in the convergence plot or the progress plot. Let us see one more time how quickly it has converged. So, it is already just after the 50th generations, the RGA has converged to the optimum solution. Now, with this, let us come to the closure of this session. In this particular session, we have discussed various operators for RGA. We found that the selection operators which we have discussed earlier, that are also applicable with the RGA without any change. Thereafter, we have discussed series of crossover operators, starting with the linear crossover operator, followed by the blend crossover, so BLX alpha. We discussed SBX crossover, and thereafter fuzzy recombination operator. These three crossover operator says that the new solution that is created proportional to the difference between the parent solution. So, that is why their search was found to be adaptive. Thereafter, we have gone through unimodal normally distributed crossover operator, which use the ellipsoidal probability distribution. The important part which we discuss is the properties of the crossover operator. So, when we want to generate or we want to develop a new crossover operator, two desired properties were discussed, such that the mean should remain the same, and to keep the diversity, variance should not reduce. Thereafter, we also discussed about a very good study on the similarity of the crossover operator that suggests that these three crossover operators, they behave very similar, only we have to find that characteristic parameter value, so that these three operators can behave similarly. Thereafter, we discussed mutation operator. In this particular list, we have gone through the random mutation operator, followed by the non-uniform mutation operator. In this particular mutation operator, non-linear probability function was used. Then we have a normal distributed mutation operator, in which Gaussian distribution was used. It is considered as one of the simplest mutation operator to implement for real numbers. Finally, the polynomial mutation was discussed in the list of mutation operators. The working of RGA and the simulation of RGA was shown with the help of 4 examples. So, we have seen that the Rosenbrock function, Hamel-Blau function, Rastrogin and Acles function, RGA was found to be good in finding or searching the minimum solution. With Rosenbrock function, when we increase the number of variable, the performance is we have to check the performance and the parameter of RGA has to be changed. For Himmelblau function, we found that since it is a multimodal problem, then RGA needs some changes so that we can locate all 4 minimum point. In the present case, RGA converged to the 1 minimum point out of 4. For Rastrigin and Ackley function, RGA was found to be good, and when we take 10 number of variable for Rastrigin function, the solution found by RGA was close to the optima, but not reached the optimum point. So, in this case, the population size or the number of generations can be changed so that RGA can work for such kind of problem. With these detail, I conclude this session. Thank you very much.